Okay, today in this lesson, we are looking at taking data and making predictions based on that data. In a previous lesson, we looked at different types of function families. You know, you have lines, you have quadratics, you have cubics, you have cube roots, and you have exponentials, and you have logarithmics, and there's sine, cosine, and tangent, and there's all these different function families that represent different types of relationships in the natural world. So when we collect data, often our data, our scatter plots, end up looking like one of those shapes. Does it make sense? Maybe I collect data about the temperature. Maybe I collect data about the temperature, right? Over the course of a year. What do I notice? It goes up, it comes down. It goes up, it comes down. It goes up, it comes down. Over the course of a couple years, maybe. So what do I learn? Well, obviously that's a function of the season. You know, summer, the temperature's up. Winter, the temperature's down, and so forth and so on. What function family probably represents that situation really well? Does anybody remember?
The snake one, right? I don't know. I wasn't listening. I'm so sorry.
You could. I'm saying that the real world.
Wait.
In the real world, there's data such as temperature that you might collect. You might collect temperature over the course of several years. The temperature goes up, the temperature goes down, and up and down, and up and down, and up and down. What function family from the previous lesson probably represents that situation? Does anybody remember? It's not something that you focused on. It's not something that you've done much with as an Algebra 2 student. Sine, yeah, sine or cosine. It's one of those trig functions. It's a wave, right? We sound waves, and we talked about multiple things that the sine graph will represent. But that's what we're doing here. Maybe it's temperature that we're collecting, or maybe it's some other bit of data, but often the data that we collect, if we make a scatter plot out of it, it ends up looking a certain way. And so what we want to do is find the equation of the line or the curve that goes through that data. Raise your hand if you've ever done a best fit line before. Raise your hand if you've ever drawn that. I'm sure, Amaya, you probably asked your teacher for a ruler on that day, right?
I always ask for a ruler.
Of course, you know, because you got all the data, the scatter plot, all drawn out, and you want to run a line directly through the middle, right? Okay. Well, that's exactly what we're doing today, except we're going to use that line, or the parabola, or the exponential function, the graph. We're going to use that in order to make a prediction about the future or some other data value that we didn't collect. Does this make sense? That's what we're doing today in this lesson. So we're going to go ahead and start looking at some of these things here. First of all, a scatter plot is a representation of data that does not fit perfectly into a function. The points show the general relationship between the two variables. That relationship can be a positive, negative, or there's no relationship. Okay? Positive, a negative relationship, or none. I found a cartoon. Has anybody ever seen the Family Circus cartoons? Anybody ever seen that in the newspaper? Okay, so here's one. It's been a long time since I've looked at the Family Circus, so I don't even remember these people's names. But the little kid says he's in an airplane seat, and you see him shaking a little bit, and he says, "I wish they didn't turn on that seatbelt sign so much. Every time they do, it gets bumpy." Now, in the kid's mind, what is he thinking? He puts on the seatbelt, what happens?
You get some turbulence.
Turbulence. It gets shaky. And so he's thinking that if I would just not put the seatbelt on, then everything's going to be smooth and everything's going to be cool, right? And see, he has this cause and effect sort of relationship going on in his head, but in reality, it's not putting the seatbelt on that causes the shakiness of the plane, is it? Okay, so the first skill here that I need you to master, the first skill that I need you to master is the concept between the difference between correlation and causation. To say that two variables are correlated is to say that there's some sort of relationship between them, positive, negative, or just some sort of relationship. However, to say to use the phrase causation, or to say anything about this causes that, it's that one variable creates a change in the other variable. Okay? So, now, is this particular example of the little boy, is this correlation or is it causation? He thinks that it's causation. He puts the seatbelt on, and then because he put the seatbelt on, the ride got bumpy. But it's not causation. It's just that there is a relationship that every time he puts the seatbelt on, it gets bumpy. Yeah, it just so happens to be that they're going through turbulence. Okay, so we'll just. I don't want to waste a whole lot of time with this. So you can look over these notes yourself, but let's take an example here. Well, let me do this because this is about correlation. So let's say X is the number of cars you buy. Cars bought. And Y is the amount of money you spend. Money spent. The more cars you buy, the more money you spend. Do you agree?
Yep.
This is a positive correlation. Is there any sort of causation there? Does one cause the other? If I buy more cars, does that cause me to spend more money?
Yeah.
Yeah. So there's a causation here. Let's say X is still cars, okay? But now Y is your bank account balance. So with each car you buy, your bank account gets smaller and smaller and smaller. Okay? As X goes up, Y goes down. Here, X went up, Y went up. There's a positive correlation. Here, it's a negative correlation. Okay? That's correlation. Can we talk about causation here? Does one cause the other?
Yes.
The more cars I buy, my bank account gets smaller and smaller and smaller. So this is also causation. Example 3. So here's a less idealized example. Let's say X is the shirt size and Y is the shoe size. As one goes up, so does the other, right? I mean, what happens to a little kid, right? Their shirt size gets bigger and bigger, but also somebody does some research and realizes, hey, their shoe size gets bigger as well. So, is there positive or negative correlation here? Say, positive or negative correlation in this case?
Or positive.
There's positive correlation. There's positive correlation. Is there causation? Raise your hand if you say that the shirt size, and an increase in shirt size causes an increase in shoe size. Raise your hand if you believe that. I don't see anybody raising their hand. Raise your hand if you believe that a shirt size increase causes a shoe size increase. Nobody's raising their hand. It's because it doesn't, right? So there is a positive correlation here, but no causation. So you can have correlation, but not causation. It's like the kid in the Family Circus cartoon. You can have, every time I put my seatbelt on, does that cause the turbulence?
No.
No. But they do happen to be related. Does it make sense? Causation means that one thing will cause the other. If you exercise, the calories burned per minute increases. If you exercise, calories burned per minute increases. So what is this? What's the outcome here? What if you were going to say this is causation? Is this causation, or is it just correlation?
Causation.
When you exercise, calories burned increases. Yeah, it's correlation. Is it causation? Oops.
Yeah.
Causation also exists because the exercise causes the calories to be burned. Good. So what about here? The number of firemen fighting a fire increases as the size of the fire increases. Correlation, right? Causation? Does the number of firemen fighting a fire increase as the fire increases? Is that a causation? What about recently in Gatlinburg? Could that fire increase and no one come to rescue? Was that a possibility? Yeah. So what really caused the firemen to go and I mean, from all over the country to come and help save Gatlinburg? Was it the fires?
No, it was like.
Or was it their humanity? And was it, a job to do? You see what I'm saying? Like, the number of firemen fighting a fire and the size of the fire, they both increase. There is a positive correlation here, but does one truly cause the other? Is every time I put my seatbelt on and then the ride gets bumpy, I mean, does the seatbelt cause the ride to get bumpy?
No.
No.
The road does.
So every time there's a fire and it grows and it grows and it grows and more and more and more firemen come, does the fire increasing cause? Is it the root cause? Is it the reason why more and more firemen come? Well, I think there's a relationship there, but I don't know that. I mean, I'd say that we could light a fire somewhere off in the boonies. Nobody knows about it. The fire gets bigger and bigger and bigger, and not a single fireman come. Is that possible? Mm-hmm. Right. So the fire getting bigger does not cause more and more firemen to come. There's something else that's involved here. Do you understand? That helps. That helps. What does the rest of this say? And likewise, the reverse, the way this is written, although there's a positive correlation, causation does not exist. Bringing more firemen does not cause the size of the fire to increase. And I don't know if that's necessarily the way we were reading it, but that's the thing. What causes the other? Does more firemen cause the fire to increase? Does the fire increase cause... It could go either way. But there's more things involved here. All right, so next. Correlation coefficient. As we look at data, we measure data. So we've got X data and we have Y data, and those are joined together somehow, and we make a scatter plot. As it turns out, the more those scatter plots are in a straight, exact line, perfect line, the closer they are to a perfect line, the R values, which is the correlation coefficient, R ranges from +1 to -1, and it's any value in between. So a correlation coefficient is used to represent the strength of the relationship. Between the data. So the correlation coefficient is represented by R. Okay? Now, this right here is crucial for you to know. We're going to use this in every single problem that we do in this lesson. R values range from -1 to +1, and check this out. The closer they are -1, +1, the closer they are to 1 or -1. It's the absolute value of R. Nick. If the absolute value of R is greater than or equal to 0.75, then we're going to say that's a strong correlation. If the R value is somewhere between 0.75 and 0.5, we're going to say it's weak. So here it's strong, here it's strong, and then it's weak, in between -1 and +1, from 1 to 0.75, it's strong, and then 0.75 to 0.5, it's weak. And then anywhere below 0.5, there's no correlation. We'll look at more examples of that in just a moment. Once you have figured out the relationship, you can write an equation. That is a general relationship of the data. This equation is called the regression equation. And that is kind of the key next step here in this lesson. So, this little part of the lesson here was just to introduce the concept to you of correlation, and for you also to realize that correlation does not imply causation. So let me state this one fact, and I need you to put this in the margin of your notes somewhere. Correlation does not imply causation. Two things can be related, but one does not have to cause the other. I think in our core we understand that. For example, I have a brother. We're related, but he didn't cause my existence, nor did I cause his existence. We're related, but we don't cause one another. Right? So, I need you to understand this fact right here. And I also need you to understand the correlation coefficient, which is the R value. And it ranges from -1 to +1. The closer it is to -1 or +1, the stronger of a relationship it is. Okay? As you move more and more towards 0, then you move towards no relationship at all. Okay? We'll look at more examples of these concepts later, but we're going to move now into the next lesson. So thank you for watching this video.